Well, hello. I'm going to make a little screencast of number 15 on page 487. This problem here is called the common ion effect problem. And you have to deal with this common ion it's talking about. Let's read the problem. It's problem number 15 right here. It says, what is the hydronium ion concentration in the solution of 0.150 molar in HNO2? So that's kind of like a typical problem, but then it adds this little piece here, and 0.0300 molar in Na-NO2. This is a salt here, and it completely dissociates. So whatever the original concentration of the salt is, the NO2 ion is going to have the same molarity. So, and we also need to refer to table A9 for the Ka value, which I've already retrieved. So you just look over there and you look up HNO2, and I have it written down as 4.6 times 10 to the negative fourth. So let's start this problem, and we can solve it and then go from there. So let's see. I have a page open. So let's start by writing down what we typically write down is our reaction in this case here. So this is problem number 15. And it looks like this. It has this HNO2. HNO2. We're going to add it to water. And then it breaks up a little bit of hydronium. And then NO2 ion. Sorry about that. Make it a little nicer. There it is. Well, it looks even still needs a little bit of correction on that. Trying to make it legible. Alright, so then we have our three rows. The first one is the initial, and then we have our change, and then we have equilibrium. So initially in the book it said that we have a 0.150 molar concentration. Remember, water is constant, and then we don't have any hydronium or NO2 ion. So we don't know what the change is, so if we don't know what the change is, then we can just write in a negative x, minus x from this first HNO2 because it will go down, whereas a hydronium is going to increase, and so will NO2. At equilibrium, it looks like this, 0.150 molar minus x. And then this is going to be 0 plus x, so this just becomes x. And so does the NO2 ion. Just like normal. Okay, here's the catch. Here is the catch. So it looks like this NaNO2 ion, compound dissociates, completely dissociates, and it makes a sodium ion and the NO2 ion. So what I was talking about before is that if I have this initial concentration of 0.0300 molar, because it breaks up and dissociates completely by the time that you go from beginning to the end. Remember, at the start it's at 0, but then it completely drains on out, and then this would completely increase. That's a little sloppy again, I apologize. 0, 0. So what has happened is that it went from here and broke up. Sodium, by the way, increases also. Remember, it's these two ions that make up the one compound. So whatever that you have as the original molarity is going to be the molarity or the concentration of the NO2 ion. So this is going to be added to our X right there. So it should look like this. It should be X plus 0.030. Okay, so that's the only real trick. That's the only real trick. So let's go ahead and generate a Ka expression. So here it is. It's going to be our products, which is going to be our hydronium and our NO2 ion, all over our initial acid, which is HNO2. Okay, So now, like I said, I looked up our Ka value. So I'm going to rewrite this expression on another sheet, and I'll refer back to this one here. So let me open up another sheet so we have more space. Okay, so let me rewrite it so that we can have a little something to go off of. So it should be our hydronium and then our NO2 ion, which has been added to by the salt, and then our weak acid HNO2. Okay, so here we go. I'm going to plug it in. I looked up on that table A9, and it should be 4.60 times 10 to the negative fourth. That's from that table A9. That's what the Ka value is for HNO2. So then I'm going to plug in for hydronium. Let me go back. I'll look back at that one sheet so that you can take a look at it. Here it is. So remember, hydronium is X, and then NO2 is X plus 0.03. All right. So for H3O, for hydronium is X. I don't know what's going on today. There's X. And then for our NO2 ion, it should be 0.030 plus X. There we go. All over, and remember, it was 0.150 minus X. And if you're wondering where I got that from, let's go back to that sheet, the first sheet. So here it is, right here. This 0.150 molar minus X. So it's minus X, that's the change, this increase by X. The only difference is this guy here, NO2, which says X plus 0.03. All right, so now that we have that all squared away, we can go on and we have to make an assumption. So I'm going to look at the original. I'm going to make a comparison. So over here, my original molarity was 0.150 molar, right? Or 1.5 times 10 to the negative 1 molar. And then my Ka value is 4.6 times 10 to the negative fourth. So I'm looking here at this negative 4 and this negative 1, and it is greater than 1,000 times. In other words, the Ka value is 1,000 times smaller than that of the original initial concentration. So therefore, what it means is this X here and this X here can go away. They can get tossed out. And the reason being is they're so small and they are insignificant. They will not change the value of the problem. So let's continue on. And just if you need to go over that again, it's the difference of those exponents. If it is 3 or more, meaning that's 1,000 times difference, then you can get rid of or discard this change. That X is so small, it won't affect the larger number. It's so small. It's so tiny. So we're just going to continue on. I'll rewrite it. It should look like this. Is equal to X times 0.030 divided by 0.150. All right, I'm going to multiply 0.150 on both sides. And then so this cancels out. And I get 6.9 times 10 to the negative fifth. And then this is going to be equal to 0.030 times X. Divide both sides by 0.030. And I end up with 2.3 times 10 to the negative third molar is equal to X. I'm going to circle this because what's the question? The question, I'll go back to the page. Here's the question. The question asks for what's the hydronium ion concentration? And so if we go back to that original sheet, we said here's the hydronium, we're looking for this X, right? This X right here. and x is x. It doesn't matter which x you're looking at. They're all the same x. And so at the end of this here, 2.3 times 10 to the negative third, that is the correct answer. I hope that helps you out. That's problem number 15. And just remember, I think the thing to remember is this portion up here is comparing the Ka value to the original concentration. And if the Ka value is that much smaller, 1,000 times smaller, then you can ignore the x. That makes life a lot easier. So that's it, kids. Good luck on your test. I'll see you later.